I'm David. I'm a PhD student from Tel-Aviv University, and I'll briefly explain our work about efficient query caching. This is joint work with Shahar Etzhaki and Noam Donetsky. So, as we all know, constraint solving is a main bottleneck in symbolic execution, and a common mitigation for this problem is simply caching queries. So, query caching works as follows. Given a query queue, we first normalize it to a query queue prime, and then we check our cache. If we have a miss, then we solve queue prime and store the results in the cache, and otherwise we have a hit and we can reuse the previously computed result. But the problem is that this scheme is not perfect, which means that there are queries which are accuracy satisfiable, but can't be reduced to the same normal form, which leads to cache misses. This happens, for example, in queries that depends on address expressions. So let's have a look at these two queries, which are generated in two different paths in this program below. So one path doesn't take this first branch, and the second path takes this branch and allocates some additional memory objects. So these two paths have slightly different sequence of allocations, which eventually results in syntactically different queries. But note that actually these queries are identical up to those constant address expressions, and actually they're also accuracy satisfiable. But again, since you don't have the same normal form, standard query caching doesn't help us in this case, and we have a cache miss. So our goal is to efficiently apply query caching for these kind of queries, and we're going to do it by modifying the expression encoding and then use a specialized matching algorithm. So for the first part, we're going to use the relocatable addressing model where the base addresses are symbolic values instead of concrete values, and each symbolic state maintains a set of address constraints which help to avoid overlapping of different objects. So if we look, for example, at our first path, then the base address of array will be beta 1, and the base addresses of the two objects allocated in the loop will be beta 2 and beta 3. This will be our address constraints on the right. And the queries that we saw before will be now encoded in this form. So as you can see, the constant address expressions are now replaced with the symbolic values beta 2 and beta 3. So now, assuming that the pointer arithmetic in our program is well defined, we can use the following algorithm to decide if two queries are accuracy satisfiable. So first, we check that the queries are identical up to those symbolic base addresses, which is the case here. For example, beta 2 from the first query corresponds to beta 5 in the second query, and also beta 3 matches beta 6. And then in the second step, we need to check that the induced address spaces are isomorphic, which means that for every matched object, we need to check that the corresponding memory objects have the same size. So in this case, the size of MO2 is equal to the size of MO5, and similarly, the sizes of MO3 and MO6 are equal as well. So in this case, we can conclude that Q1 and Q2 are accuracy satisfiable. So we implemented this approach using KLEE. We evaluated on several benchmarks, and we were able to get some nice performance improvement, more cache hits, faster analysis time, and lower memory usage. Thank you.